So we're going to do one that has more of a mathematical perspective with an equation. We're going to talk about a little bit of function, and we're going to use some isolation techniques that you covered in grade 9 to kind of answer our question for us. So let's take a read first off, and let's see what we can do here. So we have an equation. It's using the variables v and d. So v is equal to negative 0.08. D plus 50 represents the volume, v, liters, of gas remaining in a vehicle's tank after traveling d kilometers. The gas tank is not refilled until it is empty. All right, so we got a couple things going on. Let's just go ahead and describe the function. Write the equation in function notation. So let's go ahead and let's describe this as well. So we know that in this case, we should be able to kind of figure out that v is going to be our dependent variable. I know the question doesn't ask for us, but this is always a nice little way to kind of think about stuff here. The amount of gas that's remaining in the vehicle must depend on something. And it's going to depend on d, little d, for the independent variable, d, the distance that you go. Now, this is really nice for us to kind of look at here because in our next unit, we're going to be really making equations with these two things, and just knowing which is the independent and which is the dependent is pretty useful thing to do. So having that is pretty important, and just wanted to kind of put that as an aside. So describing the function, it's basically kind of described for us. We can certainly talk about it a little bit more, but let's go ahead and let's rewrite it down for ourselves, and let's kind of do this. So let's go ahead and let's describe this. And what do I mean by describing this? Let's list off the different parts. We already know v over here, and that's kind of by itself. But really, what we should be able to articulate and kind of figure out is, what do these kind of numbers mean in terms of this? And what you want to do for this is just kind of imagine that this car maybe is parked and has gone 0 distance or 0 kilometers. How much gas should be remaining in the vehicle? And that would be 50 here. This is kind of like the initial volume of gas. Initial volume of gas. Okay, and we know that because this 50 isn't attached to d whatsoever. It's not dependent on how many kilometers you have driven. So if we haven't driven any kilometers yet, this would be kind of like our initial or our starting volume of gas. I don't really know if this is the tank is full of gas or not. I don't know if 50 liters is what the fullness of it is, but we do know that 50 liters is the initial conditions and the initial amount of gas that's in the tank. Now, negative 0.08. We don't quite know what this term represents, but we should be able to represent it, or we should be able to figure out that there's a negative sign in front of it. And this is going to essentially use up some of our volume of gas for every distance or for every kilometer driven. This is going to change into something called a rate of change later on in the unit. This is a rate of change. And this rate of change kind of links our two variables together. It links something from our first set, distance, to our second set, volume. This is the rate of change, and basically what it's saying is that you're decreasing, or you're using up 0.08 liters of fuel every kilometer. I know it's liters because that's what my second set is measured in. Volume. I know it's kilometers because that's what my first set is measured in. So it's kind of like this rate of change of we're using up 0.08 liters per kilometer driven. And that's really what this 0.08 means. Just got to kind of write that down for ourselves. Using 0.08 liters of fuel per kilometer driven. That's kind of how we can read that as well. Pretty interesting. We'll get a lot more practice out of this later on in the course, and later on this unit, and later on in the course as well. But kind of like that's how we can describe this function. Now, if we're going to go ahead and do something like function notation, what we got to realize is that v is a function of d. V, my volume, is a function of distance being driven. So our function notation for the equation basically is the equation itself. It really is the same thing, except what we're saying here is that this is function notation. I am not saying v times d. This is function notation. This is not saying v multiplied by d. That is not what we're saying here. We're saying it's v of d. V of d. That's how we kind of say this. And we're saying this v, volume, is a function of d. That's how we read this. So this is like our function notation. It is literally the same thing as our equation, except instead of just saying v, we say v of d. So we tell the reader that this volume is a function of distance, of our independent variable. Our dependent variable is a function of our independent variable. It's kind of how this goes. So that's kind of our equation in function notation. Now, the reason why we use this is so that we can answer questions like B, where it's determine the value of V600. Or V at 600, we can say that. V at 600. There's a lot of different ways to say this, but that's really what we're taking a look at. And as you can see, all we're doing here is we're replacing our D in terms of our function notation as 600. So the way that we kind of handle this is that we continue to write our equation out. And I'm just going to kind of do this in a different color just so that we can I'm just going to emphasize what we're going to do here. Is we're going to still write out our same equation, but instead of writing D, we're going to write down 600 instead. And this is what the power of function notation means. We can solve for the volume of 600 kilometers driven because we have a function that relies on our independent variable of D. All we got to do now is just crank out a calculator. I got mine beside me. So negative 0.08 multiplied by 600 plus 50. And we'll see that after we do this, we're going to get 2. So what does this number mean? Well, 2 is representing the volume of gas remaining when we drove 600 kilometers. See how it's linking these two. This is 2 liters of gas remain. And that's our volume, right? 2 liters of gas remain after driving 600 kilometers. Here is our V, right? That's our V, and over here, that's our D. And together, they go V at D. So V at 600 is equal to 2, which means that our 2 liters of gas remain after driving 600 kilometers. So kind of cool of how we're doing this function notation. We kind of did it in grade 9 without kind of knowing it and speaking about functions, but that's what we did in grade 9 with linear relations as well. Let's go ahead and let's do this last one. C. And this is where we're going to have to use a little bit of some techniques that we learned in grade 9 in terms of solving. Determine the value of D when V at D is equal to 26. So now we're saying, hey, we still have our same equation from before. V D equals negative 0.08 times D plus 50, right? Same still equation. But this time we are actually going to say V at D equals, and I believe the number was 26, equals 26. Okay, so this is a little bit different from before because we don't actually have what our independent variable is. We have our dependent variable, we have what our function is 26, but we don't actually have what our distance is, or our independent variable is. Check it out. These two things are equal to the same, right? Negative 0.08 D plus 50 equals V at D. I'm kind of reading this backwards. And I know 26 is equal to V at D. Both of these things should be equal to our same function. So what we can do is set them equal to each other. We can say that since we're setting V at D to be equal to 26, we can say 26 equals negative 0.08 D plus 50. And now this just turns into basically like a multi-step word problem in grade 9, where we have to isolate for D now. We want to isolate for D. depending on, who your grade 9 math teacher was, they might have called this a number of different things. I've heard things like SAMDEB, I think it was called, or reverse order of operations. I just call it isolation techniques. I just have always done that. So I'm just going to isolate from my term with D in it. So I'm going to subtract 50 from both sides, right? I have to isolate this term, so I'm going to subtract the term that's not having it isolated. So I'm going to have 26, and I'm going to take away 50. I always like kind of doing these in reverse, kind of like this. I don't know if anybody else kind of likes doing the subtraction like this. And then you just kind of flip the polarity of it to be negative 24 instead of positive. I don't know. I like that one. 0.08D. And again, what is this negative 0.08D doing? It's multiplying, and the opposite of multiplying, of course, is division. This one I definitely don't want to do in my head. So I'll get my calculator back out, and I'll take my 24, and I'll divide it by 0.08, and I'll see that this is equal to 300. Equals D. So in this case, what does this represent? Well, after driving 300 kilometers, we'll have 26 liters of gas remaining. We're relating our independent to our dependent. After driving 300 kilometers, we will have 26 liters of gas remaining. And that's kind of how we use our function notation and what it kind of means, of course. So there's a little bit of algebra involved in here. Shouldn't be anything too challenging. Let me know if we need to do some extra practice on just these basic algebra tasks. That's cool. I can always give you a worksheet and do some videos on that. But really, this whole function approach is a way to either get our independent or our dependent variable because it very explicitly links the two. And of course, making sure that you can understand what does it mean when I actually end up solving that. That's kind of like the applied concept of that.